The Foucault pendulum. Consider a pendulum suspended vertically of length L and aligned so that the x direction points to the east and y direction points to the north. We will denote tension of the pendulum as force T, and the components of the force along the axis x and y we will denote as Ty and Tx. Displacements from the equilibrium position will be given by two coordinates, x and coordinate y. Since we are working in the rotating reference frame of the Earth, we can write mass times acceleration as given by the tension force plus gravitational force, where gravitational force will include both gravity and the component due to the centrifugal motion of the Earth, plus Coriolis force, 2 times m times velocity cross omega, the angular velocity of the Earth. We need to write the angular velocity omega in terms of our coordinate system. If the point at which the pendulum is located is given by the polar angle theta, and the Earth rotation defines theta equals 0 angle, our coordinate system will be x pointing to the east, z pointing upwards, and y pointing to the north. Then we can write angular velocity omega in terms of the three components, omega x, omega y, omega z, to be equal to the x component is 0, there's no x component. Y component is given by omega times sine theta, the polar angle, and z component will be given by omega times cosine theta. Next, we consider small angle oscillations, x and y much less than the length of the pendulum L. In which case, we can know that the tension will be approximately given by mass times g. Or in terms of components Tx, it'll be given by minus x over L, that's the angle in small angle approximation, times mg. And similarly, for Ty, it will be minus y over L mg. Another term we need is the term that will describe the Coriolis force. We need the cross product of velocity cross omega, which is given by determinant x, y, z, x dot, y dot, z dot, and then components of omega are 0, omega sine theta, and omega cosine theta, which we will find to have component x, y dot omega cosine theta, minus component y, x dot omega cosine theta, plus z component x dot omega sine theta. Thus we have everything to find the equations of motions for the two components x and y, which will be given by x double dot minus G over L times X plus the component due to the Coriolis force 2y dot omega cosine theta, which by the way we note is simply the component z of omega, so we're just gonna write omega sub z. And similarly for the y component we get y double dot equal minus g over L times y minus 2x dot omega z. If we use the notation that g over L is equal to omega naught squared, just the oscillations of a pendulum in inertial frame, then we can rewrite these two equations as x double dot minus 2 omega z y dot plus omega naught squared x equal to 0, and then y double dot plus 2 omega z x dot plus omega naught squared y equals 0. Now here what we can do, we can multiply the second equation by imaginary I and add them together, and we'll get a new equation where x double dot plus I y double dot plus 2I omega z times x dot plus I y dot plus omega naught squared x plus I y equal to 0. We know that we can introduce new complex quantity psi so that these two equations are written as psi double dot plus 2I omega z psi dot plus omega naught squared psi equals to 0. As you can see, we're able to combine two coupled equations into a single complex valued equation for variable psi. Note that in this case both real and imaginary parts of psi matter, not just the real part like we did for simple harmonic oscillator or driven oscillator. The solution to this equation proceeds as usual. So we take a guess that the form of solution will be psi as a function of time given by, say, exponent minus I coefficient alpha t. And by plugging it into our equation of motion, we find that alpha squared minus 2 omega z alpha minus omega naught squared is equal to 0, which we find to be alpha is given by omega z plus minus omega z squared plus omega naught squared. Well, since the rotation of the Earth, omega, is much smaller compared to the frequency we would expect from a pendulum, we see that we can simply write this as omega z plus minus omega naught. Therefore, we can write the general solution to be E minus I omega z times time times C1 E I omega naught t plus C2 times e to the power of minus I omega naught t. Obviously, the coefficients C1 and C2 will come from the initial conditions.